Hi, everyone, and welcome to today's talk. So this is Vit, and he's going to be giving a talk on who is meant to be the next Pope. If you're watching this on YouTube, please like and subscribe. And I'll hand over to Vit now.
Okay, thank you very much for having me here. And today I would like to talk about conclave, the election process for a pope, and how that might relate to some mathematics. So yes, we'll start with this event or this process, and we might get to some mathematics such as Kolmogorov means or the inequality between arithmetic, geometric, harmonic mean, and do some possible generalizations of what I will speak about. So what is a conclave and how to elect a pope? Usually when a pope dies or resigns from his office, which happened just a few years ago, and then only in the 15th century, if I'm right. Cardinals from all around the globe join, and they start with the Mass and prayers in St. Peter's Basilica in Vatican, and then they continue to the Sistine Chapel where the election process takes place. And actually, we don't know what happens next exactly because the doors are closed, and no one is let in except for 2 doctors and few servants to bring some meal to the electing cardinals. And so we can only find out if the election process is going well or not from the smoke. If the smoke from the provisionary chimney attached to the Sistine Chapel is white, a pope has been elected. Otherwise, if we see a black smoke, we still don't know yet. And the first time we know about who the next pope is when a senior cardinal comes and proclaims Habemus Papam, we have a pope, and says his name. And then a crowd is cheering, many people are usually around, and we can see the pope for the first time. And you can ask 2 questions basically, given the diversity of opinions of the electing cardinals. Is the conclave always guaranteed to finish, and must a new pope always be elected? And if the answer to the first question is positive, can we predict who will be the next pope if we knew the opinions of all cardinals before the conclave? We expect that the answer to the first question from experience is positive. And actually, in the 13th century conclave, this must have been reinforced by removing the roof above the heads from cardinals so that they are not warm enough, and decreasing the supply of bread and meal. But always so far the conclave reached and pope has been elected. And to the second question, that is actually the question of the talk, if we can know who is meant to be the next pope, and we will try to argue about this as well. So how on earth does this relate to mathematics? And to be honest, that's not obvious, and you'll need to be a bit patient with me. So let's start with some definitions. We will represent cardinals by some numbers, 1 up to n, and each of them will have an opinion which will be represented by a real number in some interval I, possibly unbounded interval. And these points can be thought of as some point living in the product space of these intervals I to n for convenience, and there is a nice picture representing it. And we can then think of what happens behind the closed door, and we will start by making our life very simple. We'll imagine that there is a sequence of meetings, and at each meeting only 2 cardinals, say I and J, will meet, and when they meet they will communicate, which will be represented by some function taking the opinion of one cardinal and the other and producing some new opinion which will be common to both of them. and which they will share, because we assume that the cardinals want to reach some conclusion in the long run. So for us to be able to make some conclusions, we will assume that these functions are continuous, strictly increasing in each entry, and so-called idempotent, so that this function acting on the same elements returns the same element. And at each time, the opinions of the cardinals which meet are changed to the same opinion, as I said, and the other retain their opinions, which can be written by something we'll call a conclave function. And you can see the formula. It just summarizes the result as a function acting on the product space of these intervals. And a conclave is a discrete dynamical system on this product space specified by the conclave sequence of the conclave function. A very good way to visualize what these communications are is as if we had a string with two cardinals having opinions at each end and a common opinion as a point somewhere on the string. As we are increasing an opinion of one of the cardinals, the point in between will somehow increase continuously as we are continuously increasing. And you can imagine if we have two cardinals with the same opinion, a point in between is exactly the same. We actually can notice also that the properties of strictly increasing and idempotency imply this property that somehow the opinion of the two cardinals after the communication will lie in between the original opinions with equality if and only if they agreed before their meeting. And now we can reformulate our questions in some mathematical language. Given a conclave sequence, does there exist some consensus such that each of the cardinals will converge with his opinion to this consensus? And if the answer to the first question is positive, is the consensus independent of the details of the conclave sequence? In other words, does the consensus depend only on the initial opinions and not on the details of the conclave sequence we will take? And we'll talk about it in a while. So let's start with our first question, namely the convergence of conclave and whether such a process will lead to having a same opinions. So let's start by considering at each time the maximal opinion and minimal opinion with big and little m. We can notice by the average property of communications, as I call it, that these opinions, the maximal is decreasing and the minimal is increasing. And so we can see that by the monotone function theorem, these tend to some limits. If we knew that these limits are equal, we would get our result, but we will need to wait for a while. Because, for example, there might be some asocial cardinals who would not like to speak to anyone else and who would not like to share some same opinions with others. Imagine there are two cardinals in the beginning who do not speak to anyone else during the conclave, and these cardinals have different opinions. Then in the long run, these cardinals would retain their different opinions, and definitely we can see that all cardinals cannot converge to the same consensus. So for this reason, we come up with the next definition. We say that two cardinals I and j communicate if they communicate infinitely many often. And a communication graph G has cardinals as vertices and edges between them precisely when the cardinals I and j communicate. We call the connected components of this communication graph communicating classes, and the conclave is set to be minimal if the communication graph is connected. So from now on, we will consider just minimal conclave, which rules out the possibility of having some cardinal which would not speak to anyone else. So let's start with some easy case. When the big M, which is the limit of the maximal opinions is the endpoint of the interval we consider. Then for any cardinal I, the opinion of that cardinal would converge to this big M, and we can get the result. Clearly, if M is the lower endpoint of the interval, then also all the smallest opinions would equal to this big M, and we would get little m equals big M and get our results. If big M equals the upper endpoint, then there is a cardinal J with the opinion big M for any time k, because otherwise, because the function communications are strictly increasing, some other opinion with because the conclave is minimal, he would need to communicate with some other cardinal with a lower opinion, and that would lower his opinion. So if he meets with some cardinal and if this cardinal meets with some other cardinal infinitely many times, he will also need to have opinion big M, otherwise the first cardinal would have his opinion decreased, and as the conclave is minimal, we can induct on neighboring vertices of the communication graph to show that all cardinals have an opinion big M from the beginning, implying that they definitely converge to big M. So to make progress for the case where big M is not an endpoint and rise in the interior, we will need to make some definitions. And we will start with a definition of what I call a p-lift. Given some natural number p and some delta, a communication f, we can construct a sequence of a0 delta up to ap of delta, so that a0 of delta is this big M, and always next ai plus 1 of delta is such that when it communicates with M plus delta, you would get the previous AI delta. And similarly for the right of induced p-lift, where you just change the order of the entries inside of the function f. To visualize it, you can imagine some section of constant delta, then you have M, a0 set to the M, and a1 such that a1 and M plus delta average exactly to M, a2 and M plus delta average to a1, and so on. And it is not hard to show that if you take a constant delta, the AIs are decreasing in the index I, and that if you fix I, these AIs are actually non-increasing in delta, and if you take delta to 0 from the right, they will all converge to M. And that's actually our next lemma. Suppose that M lies in the interior of the interval, then given P inside natural numbers and a communication F, then there is some small enough delta such that for any delta small enough, the left and right F-induced p-lifts exist and are unique, so are well-defined, and moreover, they have the properties I mentioned before. Probably you'll not have enough time to prove it, even though I included on the slide. So if we have time in the end, I'll get back to the proof. It's quite lengthy, but it's nothing more than some basic analysis. And what we are interested in is the result of the whole conclave, irrespective of the details of the communications. So we will try to take minimum over all these AIs, or left or right, over all communications to construct some kind of a p-lift which is independent of these details of communications which are taken. This is possible because I'm not sure if I was clear about this, but it's assumed that in this conclave, each pair of cardinals can communicate only via finite number of communications, so you can definitely take minimum over some finite set. And it's also quite straightforward to show that similar properties would hold for these p-lifts independent of f for these alphas, and it follows straightforwardly from lemma 6, the previous lemma. And now we are getting to our main result about the convergence. So if fk specifies a minimal conclave, then given initial opinions x1, there exists always a consensus of the cardinals such that each cardinal converges with his own opinion to this consensus. And the picture shows the proof idea, and I'll try to go through the proof with you. So lemma 4 resolves the case where M is an endpoint of the interval I. So we can assume that M lies in the interior of I and prove the following claim that each cardinal has an opinion converging to big M. Suppose not, then there is some epsilon so that, or there is a cardinal I whose opinion will always be far away enough from M. And also, this cardinal is assumed to infinitely many times come close to M, which must happen by the pigeonhole principle because, well, MK are going to M. It's always one cardinal which exactly has the opinion of the maximum MK, and there are finitely many cardinals, infinitely many time steps. So that's our cardinal I, and we know that there is epsilon 0 bigger than 0, such that this cardinal also infinitely many times goes away from this opinion M. As M is in the interior of I, as we assume, we can also take some epsilon 1 so that M plus epsilon 1 lies in the interval I, and we can construct a p-lift alpha 0 up to alpha p for some given p, a function of the initial number of cardinals which exists and is unique for sufficiently small delta. Moreover, by the properties, we know that alpha j delta goes to M as delta goes to 0 plus, which implies that we can restrict our attention to sufficiently small deltas so that for any j, alpha j of delta will be bigger than M minus epsilon 0. Now we will fix delta to be minimum of the epsilons above, and as the big M case, the maxima go to M, by definition we can choose k large enough such that every maximum will be smaller than M plus delta. As there are infinitely many k's, choose 1k which will be bigger than this big K. And then as xi k is smaller than mk and then smaller than m plus delta is smaller than m plus epsilon 0, we must have some xik, we must have xik smaller or the same than m minus x0. That's one of the orange dots in this diagram. And also the other cardinals have opinions at most m plus delta. So let's have a look what happens next. Now we will consider the intervals constructed from the p-lift, which are denoted here in purple as a1 up to an times n minus 1. And we know that there are n minus 1 cardinals having an opinion in these intervals. And so if we construct intervals S1 as the union of the first n minus 1 intervals, next n minus 1 and next n minus 1, we have as n intervals and n-1 cardinals, so by the pigeonhole principle, at least one of these unions does not contain an opinion of any cardinal. And we will call such a place we will call the intervals ai constituting this b1 up to bn-1 as in the diagram. And we know that there are no cardinals having an opinion in them. There are at most n-1 cardinals having an opinion above this threshold, and there is this cardinal in the orange which is below the threshold, but we know that at some point he must get up there. And this already starts looking that we might get some contradiction, and we can prove a subclaim that we can always derive a contradiction if we have n prime smaller than n number of such a sets b1 up to bn prime containing no opinion of any cardinal, and prime cardinals having an opinion above it, and all other cardinals having an opinion below. Then we can obtain a contradiction. Clearly, if n prime is 0, we have a contradiction, and then we can have a look. The orange cardinals, if they communicate among themselves, they will remain up there in this set. Orange cardinals, if they communicate among themselves, they also stay down there. And if there is a cardinal down there and up there, and they meet, then we can check by our definition of what a p-lift is, that their opinion would exactly match and would lie in the set bn prime. And so we will reduce the number of opinions up there, and we can continue inductively, which is precisely what happens here. And the important step is noticing this inequality of the opinions, where the opinion of the two cardinals, one orange and one green, who meet will be below this threshold, and you can continue with your induction. Hence you get a contradiction, which is what we wanted, and hence prove the theorem. So the theorem gives us a positive answer to our first question about conclave, and we see that generically the conclave shall terminate. And it's also not difficult to understand the dynamics of a non-minimal conclave, because there is some mixing period where the cardinals can come and meet and share their opinions, but after a while they will only communicate within their communicating classes, which you can think of as some minimal conclave. And within that communicating class, they will always reach some conclusion. And finally, you can notice that the consensus of this conclave generally depends on two things. One is the conclave sequence, and the other is the initial opinions. So if we fix the conclave sequence, we can think of the consensus as a function of the initial opinions, as a function from I to n to I, the interval. And that will be our next theorem. And we can see that if we think of consensus this way, this function is continuous, non-decreasing in each entry, and idempotent. So for continuity, you can start by thinking of a distance induced by the metric considering the maxima, and then suppose that if you have some opinion in the interval I and epsilon bigger than 0, we will want to find delta such that whenever the opinion is close enough to x1, the consensus will be close enough. And so what we do is we notice that big mk and little mk converge to 0 because the opinions of any cardinal converges to the same limit. And we can hence bound this difference by epsilon/3 for large enough case. And then as any communication is continuous, we can pick delta such that if the initial opinions are close enough, so will be the opinions of the k-1 communications. And this implies that you can bound the distance between the maximal and minimal opinions of the two conclave with different opinions x1 and y1. And since these opinions, since the consensus always lies between little mk and big mk, you can you can find these inequalities and see that indeed you have this distance between consensus smaller than epsilon, or sufficiently small distance between the initial opinions. To see that the consensus is a non-decreasing function, you can notice that by imagining two conclave, one starting with opinions x1, the other with starting with opinions y1, and because the communications are strictly increasing, if you start with with opinions x1 smaller than opinions y1, you would always preserve being with your opinions lower than the other during the conclave, and hence the results hold for the limit. And idempotency follows straightforwardly by idempotency of communications. It is actually an open question I was not able to answer so far, whether you can see that the consensus is strictly increasing in each entry. And if there is a proof, it shall probably involve proving that the minimum of the opinion starting a bit larger is at some finite time bigger than the maximum of the opinions starting a bit lower. And you can definitely make this proof for some special cases of opinions. For example, when all the opinions are same and in the other conclave, one of the opinions of the Cardinals is bigger. There is one other comment. We can think of this as a whole as a discrete dynamical system. And it's not hard to see that the fixed points of this dynamical system are precisely the diagonal, where all the cardinals have the same opinion. Then conclave does not do anything to it, right? Because they already all agree on the choice of the pope. And we can see that theorem 9 says or implies that this line of fixed points is a global attractor. And actually, the theorem is a bit stronger than that, because it says that you are not only attracted to this set, but you are always attracted to some specific point within this set. And similarly to communications, the properties of increasing property and idempotency property imply some kind of average property of consensus. So let's move on to the more interesting question, whether we can actually predict who will be a next pope. And to formalize it, imagine that there is some set curly f of all possible conclave functions, and we will restrict our attention to a conclave family of all conclave sequences such that the conclave functions are in this curly f, and the resulting conclave is minimal. And we will say that a conclave family curly C admits a type 1 constant of motion if after applying a conclave function, the result of applying the constant of motion to the opinions is always the same. and C is continuous and idempotent, or we call it a type 2 constant of motion if we again have this invariance property for any communication, and we also have some kind of an average property. Given a conclave family C, the consensus is independent of the conclave sequence precisely when this conclave family admits a constant of motion C. And moreover, if one of these holds, then C is equals this consensus, and we will call it a conclave mean. So to see this, if we have some constant of motion, we will firstly try to show that if we have some constant of motion, then the consensus is independent of our choice of conclave sequence. So we pick a conclave sequence, and since the conclave sequence is minimal, there always exists the consensus by the previous theorem. We can see that because C is invariant under any communication, we can construct a constant sequence Cxk. If we have a type 1 constant of motion, we can argue that because C is continuous and these opinions go to some limit, then so does by continuity Cxk go to this limit. By idempotency, we can argue that this limit equals x equals as if we acted by a consensus. And then because we know that Cxk is a constant sequence, it clearly equals by uniqueness of limits to Cx to the consensus acting on x1, and because x1 was arbitrary, we get the equality between C and x between the consensus, and because clearly the constant of motion was defined to be independent of x1, so will be the consensus. If we have type 2 constant of motion, we can argue similarly, but again by these bounds, to see that the little mk and big mk go to the consensus and also so does Cxk, and argue that again these must equal and C is independent of x1, so must be the consensus. The other way around, if the consensus is independent of our choice of conclave, we can define the constant of motion C to be precisely this independent consensus. This is well defined, and then by the previous theorem we see that it has the properties of both of the types of constants of motion. So this in particular shows that type 1 and type 2 constants of motions are equivalent because they both equal to this consensus. And an interesting thing is to see that you need to have some additional properties to not only the invariance as one would expect to make this happen. And these properties somehow nicely match those properties of consensus in the previous theorem. A bit more conceptual look on this might bring us to the Nethers theorem in Hamiltonian dynamics, because in Nethers theorem it says that there is, if we have some freedom to choose time origin or space origin or axis direction, this corresponds to some conserved quantity like energy momentum or angular momentum. By this theorem, the freedom to choose the conclave sequence corresponds to having a constant of motion. but one shall pray not go too far with this similarity, because we are dealing with a discrete dynamical system which does not have really a Hamiltonian, and we cannot consider invariance of some Lie symmetries of this Hamiltonian, right? So, but we can see that in the language of dynamical systems, these constants of motions are some kind of extra Hamiltonian-like structure or function of the dynamical systems. And we can see that, or from experience in the dynamical systems theory, these are usually quite rare. And this brings us to the fact that very likely not many conclave have these constants of motion and are not really well predictable, which implies why we always see the wow effect of the crowd cheering, and why we cannot really say who is meant to be the next pope. And now we'll move on to the more maths bit and relate this idea to Kolmogorov means. These means have been invented, are actually a very Cambridge topic by some people. It's claimed that they have been invented by Hardy from Trinity, but I'm not really sure, because the book which mentions them was published in 1934, and the paper on Kolmogorov means by Kolmogorov was published in 1930. But maybe one of you knows how it actually went during history, and you can tell me at the end of the talk. So what is a Kolmogorov mean? It's a function from an interval to an interval. Well, we suppose there's a function f which is continuous injective function on an interval I, and then the Kolmogorov mean on an n numbers x1 up to xn is defined via the formula as you see. Because f is continuous and injective, it must be strictly increasing or decreasing, and because there is always the freedom to alter the function f by multiplying by a constant or adding some constant, we can, without the loss of generality, take a strictly increasing function f. And if we want to signify that we talk about a mean on n numbers, we will write the n out there. And finally, a very important class of these means are the so-called power means, which are induced by functions x to p, or the logarithmic functions. These include the arithmetic mean for p equals 1, geometric mean for if we take the logarithmic function, and a harmonic mean if we take p equals -1. And as proved by Hardy, Polya, and Littlewood, these are the only homogeneous Kolmogorov means. We can see that there are few interesting properties of these means. Firstly, they are always continuous, strictly increasing in each entry, idempotent, and if we replace few first entries by means of these few entries, then the mean of all the entries is always the same. And we can also see these functions are symmetric under the permutation of the entries. And now we will relate this these Kolmogorov means to our previous discussion of conclave means, showing that any Kolmogorov mean can be thought of as a conclave mean, i.e. an independent consensus. So given a Kolmogorov mean on n numbers induced by some function f, we will think of a family of possible communications so that the communications between any two cardinals will be by a mean on by a Kolmogorov mean on two numbers, and then by the first properties in the previous lemma, we can see that we have well-defined conclave functions, and we can also see that big M f of n provide a constant of motion for this conclave family with conclave functions in curly F by one of the previous lemmas, and hence we can see that these MFs can be thought of as conclave means. Because in this case, if two cardinals meet, they will always communicate by the same function, namely the Kolmogorov mean on two numbers, it suffices to prescribe a meeting sequence of the pairs of cardinals to describe a conclave. And a partial inverse to this theorem will be given a bit later in this talk. Now let's jump into some intermezzo of inequalities, and I'll try to persuade you that we can make a very visual proof of the arithmetic mean, geometric mean, and harmonic mean inequality with basically no algebraic step. Imagine having two conclaves where the communication functions will be given by Kolmogorov means on two numbers as described before. Then if one of and we will have two conclaves, one generated by Kolmogorov means with function f, and the other with Kolmogorov means generated by function g, and such that the means of two numbers always have inequality between them, then we will be able to see that as the conclave proceeds, you will always have this inequality preserved, and therefore even the consensus as a limit must have this inequality because it was there right from the beginning. So we are able to generalize if we have inequality between two Kolmogorov means acting on two numbers, we automatically have inequality between two means acting on n numbers. And then it suffices to prove the arithmetic mean, geometric mean, and harmonic mean inequality on two numbers. And for two numbers, we can make this figure and use a bit of Euclidean geometry to see that if we have numbers x and y, their arithmetic mean is just the radius, the geometric mean is by the Euclid's theorem right over there, and by considering some similarities of triangles, you see that you have your harmonic mean over there. So the usual arithmetic mean, geometric mean, harmonic mean inequality follows quite easily. Either for the case n equals 2, you notice that it reduces just to a square being bigger or the same than 0, or you can see the picture I showed you, and then the statement for arbitrary n follows by the previous theorem. And there are a few remarks. Firstly, that so far in what I tried to do was to argue everything analytically and geometrically, so that each of the steps I've done could be visualized, and this leads to some kind of a visual proof of this inequality. And but, well, everyone likes different proofs, and you will definitely have your favorite proof for this theorem. But there is something more subtle we will use later. It shows us that the conclave mean is built from the conclave functions, which depend only on communications, i.e. means between two numbers. And hence properties of conclave means shall be somehow inherited from these communications. Stated even more vividly, if something holds for means of two numbers, it shall better hold for means of any n numbers. And this intuition will be later in our next chapter on Kolmogorov's theorem. There is a theorem from 1930 which tries to classify the Kolmogorov means by their analytical properties. And actually the properties I mentioned in the previous lemma, i.e. continuity, strictly increasing means in each entry, idempotency, symmetry and repermutation of argument, and this replacement property where you replace few of the entries by their means, and then you compute the whole mean. These properties uniquely determine the structure of the mean and imply that there must be some function f which generates these mn as Kolmogorov means. There are definitely some setbacks to this theorem because you need to assume a whole sequence of Kolmogorov means from M2 up to any Mn and further to make your proof. And this is not really nice, especially the property which makes this difficult is the replacement property, which somehow couples means of any size. And that's what makes this problematic. First try to overcome this was by Aumann, but he needed to assume further that we restrict our attention only to F analytic. Much better result was then given by Askel, and where he was able to somehow change this property 5 to a different property, as you will see shortly, and then to get rid of this coupling between various means. And this was generalized by Munich, Maxa, and Mocken, where they replaced the last property by some kind of a dissymmetry, as they call it, if I remember that right, the name of this property. We will not be able to do as good as these guys did, but we still be able to decrease the number of couplings in the last property and somehow to make the properties of the original Kolmogorov theorem weaker with our conclave considerations. So here's the stronger Kolmogorov theorem. If you have functions, again, you need to assume a whole sequence of functions, and then you know that there is some function f, so that these MNs are Kolmogorov means generated by f, if and only if you assume continuity for Kolmogorov for means on two numbers, strictly increasing property in each entry on two numbers, idempotency only on two numbers, symmetry, you again assume it only on two numbers. Then you assume the replacement property, but only when replacing two numbers by their means already. And then there are other two properties, property 6, which is the average property, as we called it in our previous discussion about conclave. It clearly follows from properties of idempotency and strictly increasing in the original theorem, and then also the property 7 that these MNs are injective in each entry while the other entries are held fixed, which follows from the property that MN are strictly increasing. So basically what I'm trying to say here is that clearly this theorem is stronger, and the implication of the properties P of the original Kolmogorov theorem imply the properties we assume in our theorem. And we'll call these properties Q. Now what we will try to do is to use our whole conclave construction to prove that actually these properties, which seem to be weaker, imply the properties P of the original Kolmogorov theorem. If n equals 2 and there are only two cardinals, properties Q clearly imply properties big P because we assume all the properties from the original theorem to hold for means on two numbers. If there are more than two numbers, we will consider a conclave family C with n cardinals, and allowed conclave functions, which will be precisely the communications of two cardinals. Then the properties 5 and 6 ensure, properties 5 and 6 over there ensure that Mn is a type 2 constant of motion, and hence by our previous theorem, a conclave mean. And then by our theorem on the consensus, we know that Mn is a consensus and is continuous, non-decreasing in each entry, and idempotent. And because Mn is not decreasing in each entry, and also it is injective in each entry, it must be strictly increasing in each entry. Actually, this last property on injectivity in each entry might be dropped if the open question on strict increasing properties of consensus are proved true. So it suffices to show that properties 4 and 5 hold. Property 4, it suffices to check transpositions. So we'll consider a cardinal meeting sequence ikjk, which specifies the conclave, and on the unpermuted opinion, this leads to some conclave mean in the limit, or each cardinal has eventually this conclave mean as their own. Suppose that the opinions xp and xq are swapped, then it's not difficult to see that if you consider the meeting sequence given by swapping also these cardinals, if it comes to them, then the underlying communication graph is still connected, and these opinions approach Mn with P and Q swapped. And because M2 is symmetric, this conclave is the same as the previous with cardinals swapped, and because we have Mn independent of the underlying conclave, we have this equality. Finally, for property 5, you imagine a conclave on the whole set of n numbers, and then you take some lower number of cardinals L, and you consider some minimal conclave G just on the set of these cardinals. And you extend this G so that it will leave the opinions of other cardinals constant. Then you suppose that some opinions, initial opinions, are given, and you will consider the conclave sequence big Hn for some given n, so that for first n minus times the gk will be taken as conclave functions, and then you will continue the conclave as if it were an f conclave. Because fk produces a minimum conclave, so does hn, and we can see that because Mn is a constant of motion, there we can apply first few and minus one communication with making no change, and hence this equality holds because gn minus 1 up to g1 converge to little m, where m is this conclave, where is this consensus. Ml, as n goes to infinity, this Mn is continuous. We can take the big N to infinity and obtain our replacement property for a general number of, or for general number L. So as I said, property, well, no, I didn't say this. Property 6 might actually be replaced by ML continuous and idempotent property, because type 1 and type 2 constants of motions are equivalent, and property 7 might be dropped if we prove that consensus is strictly increasing in each entry. As I said, this seems to be a stronger statement than the original Kolmogorov Theorem. And we can reformulate this back to our conclave language and to infer some information again about the papal election process. So if you consider a symmetric communication M2 and conclave families for n cardinals with the allowed set of conclave functions given by communicating by this symmetric communication M2, I'm not saying that it's Kolmogorov mean at this time, then if the constants of motion exists for any such a family of with n cardinals, and these are injective in each entry while the other entries are held fixed, the corresponding conclave means are Kolmogorov means. That's precisely the claim of the previous theorem, i.e., the existence of constants of motion is very restrictive about the conclave family we are considering. According to this theorem, if the constants of motion of this very general class of dynamical systems exist, they must take the form of Kolmogorov means, which supports our thinking of constants of motion as something very rare in the realm of all possible conclave dynamical systems. And I'll end up this talk by further outlook where this thinking might go on. We were very restrictive about communications. Cardinals had to share the same opinion in the end, and only two cardinals could communicate. So we could try to generalize a conclave function to something which would act so that each cardinal could share opinion with more other cardinals around him and does not need to take precisely the same opinion. So we can assume that it's updated by some function f, where each projection fi is continuous and satisfies this average property. In literature, these are often called means, and they are strict if the inequalities becomes equalities precisely when the entries are the same. This relates to what Gauss studied, where he studied a sequence starting with some initial numbers x and y, and then he updated the numbers x by arithmetic means and the numbers y by geometric means. And Gauss managed to prove this remarkable theorem, especially for his time when it was difficult to compute the integral on the right-hand side, whereas his iterative procedure was relatively easy to give an estimate for this difficult integral. And in our conclave setting, this corresponds to two cardinals using the same conclave function for all the time, one being the arithmetic and the other being the geometric mean. By Piskovsky, it has been proved that if we have such a generalized conclave, and this conclave is generated by a single communication function, then if there is a cardinal J whose communication would always be smaller than the communication of other cardinals, and this Fj is strict, then after any time this function taking initial opinion to opinions after time n is R means, in the meaning I said that they appear in literature, and there is a mean, big K, such that the conclave converges pointwise to KKK, i.e. appears as a consensus in our previous discussion, and this K is F invariant, similarly to constants of motion, and continuous F invariant mean is unique, i.e. this K is unique if it has these properties, and if M is strict, so is K. So this definitely matches nicely with our intuition that if we have no freedom to choose the conclave sequence, i.e. we are dictated to, well, no, the other way around. We have a freedom to choose any conclave function we want, and we are actually choosing just from one function, then we know that our consensus shall be independent, as actually appears in this theorem. And we can ask what happens if we route more generalized conclave function to generate such a process. Another possible generalization is to metric spaces, and to ask how to define a mean on a general metric space. And I'll just go quickly through this. If we have some k prime between 0 and 2, a uniquely geodesic metric space is called k prime convex if for any 3 numbers and a geodesic between these 2 numbers connecting x and y, and for all d we have the following inequality, which is some kind of a generalization of the parallelogram rule from Euclidean geometry, if I'm correct. And what Palfia considered is considering some starting points, some initial opinions in a complete k-convex metric space, and he defined a mean between 2 numbers to be a point exactly half the way along the unique geodesic connecting these 2 points, and then given some permutation sequence, which acts similarly as our conclave sequence, he defined new means to be such that the cardinal I takes an average opinion of the permuted cardinal I and I plus 1, where the addition is taken modulo n. And he proved that there is some consensus such that every cardinal has his opinion converging to this consensus, generally depending on the permutation sequence pi. And moreover, if the underlying space is Euclidean in the sense that it's flat, then this consensus will be independent of the sequence pi k. And we can actually, with our conclave considerations, we can prove something similar. And we can even generalize the means to weighted arithmetic means on k-convex, complete k-convex metric spaces. So if we have the initial opinions x1 up to xn in a complete k-convex metric space and some weights associated with these cardinals, then we can define a mean between x and y to be well, we define this symbol x mean y by taking going t time along the unique geodesic between x and y, and given a sequence of pairs of cardinals, we can say that the 2 communicating cardinals will have a mean where we move precisely by these weights updated. So these 2 cardinals have their opinions updated in this way, and the other cardinals have their opinion left same. In particular, if all the weights are same, this will reduce to the basic arithmetic mean. And we call the conclave mean the conclave minimal if there exists k large enough such that any cardinals, any pair of cardinals will meet during time k plus 1, k2, and k plus k for any k larger than big K, which is a bit more restrictive condition than before on minimality of conclave. And we can prove a theorem that if we have a minimum conclave as above, then there is a consensus such that any cardinal I has an opinion going to this consensus. And I could go through the proof, but I'm not sure if I have not run out of time.
Let's ask if anyone has questions before we go back to the claim. Yeah, if not, I guess you can go through the claim, or if you want to.
Okay,
or...
I might have a look on this proof down. So in the first step, what you try to show is that if you take the sequence of distances between the communicating cardinals, then the distance between the opinions of the cardinals, which are always at that time k going to communicate, will go to 0 as k goes to infinity. Firstly, you notice that for any point in this metric space y, you notice that the distance between y and the opinion of the cardinal I and j at time k plus 1 is smaller or the same than this, which is dictated by the property of what is meant by k prime convex. And the distances to this arbitrary point y are conserved or preserved for other cardinals I. Then if you take, and then you can consider the sum of all distances from this point y squared to any cardinal I, and take ek to be this number. And what we will try to show to prove the claim of this step is to show that this ek goes to 0, and then we will be done, because there are finitely many qk's, each bigger than 0, smaller than 1, and k prime is a constant, so the result will follow. And we can see that by summing these all of these inequalities, we see that ak plus 1y is more than aky minus ek. So aky are definitely always bigger than 0, are also this sequence is decreasing, and hence it approaches some constant. And because it approaches some constant, then we can also see that ek, which is bigger than a 0 and bounded above by these differences, and these differences go to 0, imply that this ek goes to 0. Next, at a given time k, if you take the maximum between the distances of opinions of any pair of cardinals, this maximum will go to 0. And you can inspect this by considering that you're given some epsilon bigger than 0 and pick sufficiently large n, such that for any k bigger than this n, you have e prime of k, which is something I forgot what that denotes. And yeah, it's actually the distance between the cardinals which will just communicate. You can take their the distance between their opinions to be smaller than epsilon over this big K, where this big K is the bound on the time when every pair of cardinals will manage to communicate in the definition of minimal conclave. Then given large enough time K, you can take a pair of the cardinals such that they have the minimal, such that the maximum distance is precisely the distance between the opinions of these cardinals. And you can consider K minus L to be the last time when these cardinals have met. As the conclave is minimal, this is bounded, and this L must be smaller or the same than K. And at that point, because they communicated, they shared a same opinion, and the distance between their opinions is 0. And because we considered this L to be minimal, we know that at every time only one of these cardinals, I star or J star, can change an opinion. So suppose that without the loss of generality, it was the cardinal I who changed an opinion at time t, and then you can construct an inequality firstly by going to the definition of K prime convex metric space, and then you then notice and make some estimates by expanding the distances between x j star and jt. And you also use that 1 minus qk is more than 1, and you get to this inequality, and you recognize that you can complete a square with this, and so you see that the distance between the opinions of cardinals between these two cardinals we consider can increase by at most this e prime of t, which is assumed right from the beginning to be smaller than epsilon over k, and at every time step, and hence during this number of time step, the distance between the opinions will decrease by less than L times epsilon over k, which is more than epsilon. And finally, we would need to have some better knowledge of how these k prime convex spaces work and some of their properties, but as is well known, you can consider a geodesic convex hull of these points at every time. And these steps I proved are sufficient to show that the diameter of the convex hull goes to 0. And then by invoking Cantor's intersection theorem, the limit is a singleton set, and then any cardinal has an opinion converging to this member, to this X bar, to this consensus in the singleton set. And that proves the claim. And you can actually show also that there is a freedom to choose any conclave, and the consensus is independent of this choice if you are working in R to N, I mean Euclidean spaces, in the sense that your X is precisely some product space of real numbers. And because then you can take projections, and in each projection you have a weighted arithmetic mean, and you can do something similar to what we did in our discussion on Kolmogorov mean. But it's open question whether this will still hold for some general flat spaces in the sense as Palfia defines it in his paper. So that's probably all I have to say, and thanks everyone for your attention.
Thanks. Yeah, that was a very interesting talk. Does anyone have any questions? If there are no questions, I guess we could end the talk here today.